Hello and welcome to this video lesson. We will be looking at a few example problems involving the limit comparison test. Our first example is asking, does this converge? And we have a series involving two polynomials being divided by each other. So we have n squared and n cubed minus n squared. The limit comparison test is an excellent tool for solving the convergence of polynomial fractions. We'll first start looking at the highest degree of the numerator, which is 2, and the denominator, which is 3. That would give us 1 over n. So then we will let sequence A equal to n squared over n cubed minus n squared, and series B or sequence B to equal to 1 over n. Series B diverges by P series since P is P series test since P is equal to 1, which is smaller or equal to 1. For the limit comparison test, we're going to find the limit of n approaching infinity of an over bn, an being the one in the question, and bn the one that we know either diverges or converges. So this will become limit of n approaching infinity of n squared over n cubed minus n squared. And I'm going to multiply it by the reciprocal n over 1 by dividing the numerator and the denominator by n cubed. We will see that this will become 1. And we know that 1 is a positive real number, and therefore by the limit comparison test, series A diverges. For our second example here, we got n squared over square root of n cubed minus 3. So we're going to look at the highest power in the numerator and denominator. That is n squared over n times n 3 over 2. And n squared is here, n is here, and n cubed is. This will then equal to n squared, the denominator n2 over 2 times n3 over 2. That is n squared n5 over 2 equals to n4 over 2 and 5 over 2, which is equal to 1 over n 1 over 2. Because of this, we're going to let a equal to n squared n root n cubed minus 3, and we're going to let sequence B equal to 1 over root n. We also know that series B diverges by P series test since P is equal to 1/2, which is smaller or equal to 1. Okay, now that I know this, I'm assuming that my series is going to diverge, but I have to show it first. So limit of n approaching infinity of an over, sequence A over B is equal to limit of n approaching infinity of n squared over n cubed minus 3 multiplied by n half. And I should have simplified this at the beginning. I don't even know why I wrote it this way. This is just n cubed minus 3 times root n over 1. To make this a little bit easier to understand for you, I'm going to rewrite this n as square root of n squared, and I will write limit of n approaching infinity of square root of n cubed. The n cubed is coming from me multiplying square root of n squared times square root of n, and I'm going to divide that by square root of n cubed minus 3. Now if I divide both the numerator and denominator by root n cubed, or n to the power of 3 over 2, as n approaches infinity, I will end up getting a value of 1. I know 1 is a real number, which is positive, it's not equal to 0, and therefore series A diverges by limit comparison test. And to recap, we saw that our series B here diverges due to P series, and since we got 1, we didn't get 0, therefore that means that A also diverges. And if B converged, if we had gotten a 1, then this would have also converged. Our last example here, we got a sequence of sine of 1 over n, and we're trying to figure out if the series sine 1 over n converges or not. And this is a little bit more challenging one because we don't really know what to compare it with. But the only thing that one of the only things that we can compare it to is 1 over n. And let's see if this works or not. I am going to let sequence A equal to sine 1 over n and sequence B to equal to 1 over n. I know that series B diverges by P series test since P is equal to 1, which is smaller or equal to 1. Now I am going to attempt to find limit of n approaching infinity of A over B, and that's going to equal to, and I'll write it differently this time. I will write it as sine of 1 over n over 1 over n. And if you notice, I will get something beautiful. I will get 0 over 0. Now I am super excited because this is an undeterminate form, which means that I have to use L'Hopital's rule. And that would be the limit of n approaching infinity of the derivative function of sine of 1 over n. So I'll do that in purple here. I have d by dx of sine 1 over x. And I have to use the chain rule here. Of derivative of sine is cosine, and the derivative of the inside 1 over x is negative 1 over x squared. And for the denominator, the derivative of 1 over x is equal to negative 1 over x squared. Putting it all together, on my numerator, I have negative 1 over n squared cosine of 1 over n. And on the denominator, I have negative 1 over n squared. This cancels out with this, and I'm left with cos of 1 over n. N is approaching to infinity, so 1 over n is approaching 0. And therefore cos of 0 is equal to 1. And we know that 1 is a number, which is not 0. It's a positive real number. And because of this, series A also diverges by the limit comparison test. So the limit comparison test is a very useful tool to test for convergence, especially if you have polynomial fractions. But sometimes even if you have a trig function like this, because you can use L'Hopital's rule, and when you do something like this, you have to use the chain rule for, and when you use the chain rule, you get the derivative of 1 over n. If this was 1 over n squared, then if you had 1 over n squared, if you were comparing this one with 1 over n squared, you will get similar derivatives and they will cancel out, and that might help you with finding whether or not the series converges or not.